So I will be talking about hybrid and dimerized structures that can host Majorana-bound states. And as Professor Wiesendanger told quite thoroughly yesterday, his group managed to create a system that can host Majorana-bound states with putting an iron atoms on rhenium surface using a changed method known for over 30 years now. And what they did was to measure the what they did was to measure the conductance, tension conductance of the edges of the system that they were building. And as you can see here, with the increase in the length of the nanowire, we can see these edge states that are getting more and more pronounced up until the nanowire that has 40 atoms. Okay. Yeah, thanks. And as you can see here, there's the topography of this pristine nanowire, and at the zero bias, we can see that there's a non-zero differential conductance, which is a smoking gun of Majorana-bound states existence. So, oops, sorry. So, in case of the theoretical ingredients needed to create Majorana-bound states, we start with the typical parabolic dispersion relation, and with the introduction of spin-orbit coupling, we get our bands that get separated with relation to momentum. If we input magnetic field to a system, we get a Zeeman gap, and that disjoins those two bands into Rashba bands. And as we input superconductivity to a system, we obtain a new superconducting gap that, after changing, increasing magnetic field, it transitions into a topological gap. And this can be seen here. So I guess the interruption will still happen. We can see this here, that this value of 0.2 is the value of topological transition in our model. And we can see here that just after the closing of the ordinary superconducting gap, we have a new opening of topological gap. And there's a zero energy level that is thought to be Majorana. So that was a change to the topological regime. And also, in case of the momentum perspective, we can see that just after the topological transition, we have a band inversion, which is a hallmark of topological transition. And as we increase magnetic field further, the region in momentum that has their bands inverted widens as well. So, sorry. So, in case of the actual creation of the system, we have a Hamiltonian that consists of three parts: the kinetic part that has hopping, chemical potential, and magnetic field, proximity-induced superconductivity, and spin-orbit coupling in 1 and 2 dimensions. Or 2 dimensions. And this model was used first in 2010, and from this we can obtain such a system, such a diagram that shows a parameters in which system is in either topologically non-trivial or trivial regime that corresponds to -1 value for non-trivial one and 1 for a trivial one. And usually we can use this condition for the transition to topologically non-trivial phase. which has Zeeman energy on the one side and hopping chemical potential and gap size on the other. However, in order to show more intrinsic properties, we have to use topological invariance, and in order to do so, we have to present our Hamiltonian in more in another way, like this skew-symmetric form. And from this, we can calculate Pfaffian, which is a sign of determinant of those block pairs of Hamiltonian taken at time reversal invariant momentas. So where we can also look for Majorana bound states. So in our case, we studied hybrid systems. So the dimensional hybrid systems, either that consist of Rashba nanowire and connected to either a 0D quantum dot, 1D elongation of the nanowire, 2D plaquette that I will be discussing today, and a nanoring. We also can find them on the edge states around 2D nanoflakes with some modifications of the Rashba nanowire, in this case with sublattice, either as an antiferromagnetic sublattice or sublattice similar to a SSH scenario. And also for a impact of substrate, superconducting substrate on 3D atomic chains in order to look for a topological transition there. And here we used bands from DFT and vanillized them in order to produce tight binding model to obtain sign of topological transition. So now for the main part, I will be discussing this system, this dimensional hybrid that links 1D nanowire and 2D plaquette. So at the beginning, we have those systems separated. So we have a 1D nanowire. These dots show the probability of localization of wave function on the nanowire, and eigenvalues. So at the zero energy, we can see those degenerate states that are linked to existence of Majoranas, and obviously we can see pronounced localizations at the edges of the system. In case of 2D plaquette that is set for a topological regime, we have a plethora of in-gap states, however, that corresponds to those corner or edge states. However, we do not have any zero energy states. So in this case, no Majoranas. However, if we join them, we can see here that a zero energy state emerges in such a system. And this is a result of the situation that we had Majorana here. However, after joining those systems, Majorana bound state was flown to the edges and corners of the system, and it localized there, and the another Majorana was left virtually unchanged. And in order to show some probable method for experimental investigation of such a system, we propose the selective equal spin Andreev reflection that could be a tool used to detect Majoranas. And from the theoretical perspective, it's a spin polarized conductance between nearest neighbors in a system. As for the dimerized part, so here we usually, when we look for the topological transition, we have this condition that I spoke about earlier. And these three parts, magnetic field, chemical potential, and gap size was usually changed in some papers. However, we wanted to check what happens if we change somehow the hopping integral. And to do this, we were using a scheme similar to the SSH model. So we introduced this delta parameter that changes both spin conserving hopping and spin flip hopping. So the model in question is shown here. We have this delta that changes the hoppings between atoms, and we correlate this to the change of the distance between those atoms. So if the delta is 0, like here, we are in the usual Rajba nanowire system. However, if we increase this value, at some value, we start to obtain a new topological regime that allows for Majorana bound states to exist far away from the usual parameters that are allowed for Majorana, so near the bottom of the band. And additionally, we can see that this modulation of hopping integral can have both constructive and destructive effect on the topological diagram. So we can see here this protrusion that allows for the existence of Majoranas at atypical region. However, if this value is high enough, we can see that there's a near complete depletion of the topological diagram. So now I will try to show you a movie. It's always tricky in this situation. So what we will have here will be, just pay attention to this dot here. We will travel across this red line with change of the chemical potential. So we will encounter a topological phase that is inherent to Rajba model and a new created dimerized topological phase. So we can see here changes. Here we have, once more. After we get into the topological phase, we have a inversion of the parity of bands that we see here. And in this case, in this phase, parities have the blue one, which relates to its value, blue one on top and the yellow on the bottom. And if we are in the second, we get out from the topological phase, so there's no transition. We are in another one, and as we can see, the parity of bands is inverted between those two phases, which relates to the opposite value of the winding number for those two phases. And okay, and as we leave this this second phase, we go back to a normal function. Okay. Lastly, I would like to tell something about the disorder robustness of this new phase. So we checked 3 points of the topological diagram. So the usual Rajba nanowire system, a bit dimerized, and the point taken from this new topological phase. And as we can see here, we have here a Anderson disorder. So the random disorder on chemical potential on each given site of the system. We can see that the yellow curve is the last one to leave the -1 value, so the fully topological system. It survives the highest value of this Anderson disorder, and this part of the plot can be seen here. So just after the value of 2, we can see that the zero energy state is no more. And from this, we can deduce that this Majoranas in this newly created topological phase are actually more resistant to disorder than the usual Majoranas from the Rajba nanowire model. And with this, I go to summary. So the Majorana delocalizes partially to connected dimensional hybrid structures like the 2D plaquette that I shown here. And this delocalization can be detected, for example, via spin polarized tunneling techniques. And also Majorana bound states can exist outside of the Rajba nanowire model, and in our case this addition of sublattice allows for Majorana bound states to emerge at non-typical values of parameters. And also this topological phase happens to be more resistant to disorder than the usual Rajba nanowire model. So these are the references for the papers that I was presenting, and thank you for your attention.
Thanks for the nice presentation.
I want to ask which simulation software did you use for this?
My own code.
It's your code?
Yeah.
Okay, good. Thank you.
Yeah. I have a quick question. You show some very nice results there with the plaquette and the 1D, let's say, wire. Is there some coupling you put, or you just put them together? So can you tune the coupling between the two? When you touch, let's say, because this is very interesting result.
It was put together by changing the value of spin flip hopping and spin conserving hopping. So if there are disjoint, its value is of 0, and as you increase.
So 0 and 1, let's say.
No. Well, it can be any value
You
between
can,
0 or
I
1.
see. You can tune it, let's say.
Yes, and in this situation, as you increase the value of hopping between in this place, you see more and more of my runaway function flowing.
Which flow in the plaquette, actually.
Yes,
Very
yes.
nice.
Quadratic forms of. Is it this model is exactly solvable? Yes, actually, yeah. Okay. Some kind of XY model, Kitaev toy model.
No, it's not. It's just the type model is more rudimentary. In this case, it's just a it's a
You
type
add
model.
some another.
Uses vanilla orbital spheres.
Yes,
Is it correct?
but
No, not really,
creation and
but-
annihilation operators. Yes, you have only creation and annihilation operators.
Yes,
only.
yes,
And
yes.
what about mu? Chemical
Chemical
potential.
It's set as a parameter. in a
Yes,
sense.
as
It's not
phenomenological.
made like in
It may be. It can be 0. Yes, or it's important.
Well, it's kind of important because your system has to be on the near the bottom of the band. However, not always, as is shown in this part about the.
But
vibration.
the
But
number
it can
of
be-
particles does not conserve. Yes, in your case,
Well,
X.
for the normal rubber nanowire, it should be depleted system, so the -2 value of.
Sorry, you should speak.
Yes,
with the
it's a-
microphone, so
Okay.
Yes. We
Yeah,
understand
I know,
each other,
but
but
someone online cannot hear.
Thank
But
you.
please
Okay,
keep
okay.
it short because
Okay,
we are
so-
all-
yes, thank you very
So-
much. It's